Myself Sukhin Sadhukan. Today I am going to discuss about two devices, thermomagnetic generator TMG and hybrid thermogenerator HTG, two caloric materials magnetocaloric and electrocaloric, and two electrocaloric materials PVDF TRFE CFE terpolymer and strontium doped barium titanate ceramics to investigate their ferroelectric and electrocaloric properties with the purpose of using them in the before mentioned devices. Now the first question is, what is thermomagnetic generator? Thermomagnetic generator are the devices to produce electrical energy from low temperature waste heat using magnetocaloric material. Magnetocaloric materials are the materials having strong correlation between its magnetic and thermal properties, especially near to its Curie temperature. In this case, the magnetocaloric material, the GD film, has the Curie temperature nearly slightly above the room temperature. The film here is held by a metallic cantilever structure, spring structure, in between the hot heat source and cold heat sink. So, in its normal state, due to the restoring force of the spring, the film gets stay attached to the heat sink. This heat sink. So now at this low temperature it's in its ferromagnetic states. So if we can place a strong magnet attached with the hot source, due to a strong attraction force on this GD film, it can pull the film towards it against the restoring force of this spring. So due to this attraction force, the film will get attracted towards the ceramics, a hot source, stay attached, tends towards its Curie temperature, tends towards the paramagnetic nature, and as well as so the magnetic attraction force decreased, hence the restoring force of the spring overpowered and pull back it again towards its cold sink. So it becomes cold again, becomes ferromagnetic again, and the cycle continues as long as this temperature difference is maintained. So here the thermal energy gets converted to the corresponding mechanical energy. Now if we can place a piezoelectric materials on the surface of this metallic cantilever spring, this vibrational mechanical energy can be converted to the electrical energy. So thus in thermomagnetic generator, the heat energy can be transformed to the corresponding electrical energy. So we have achieved the real working device here. Here it is the working device. You can easily see the white ceramics, piezoelectric ceramics is placed over the metallic cantilever spring, and the central is the it is the magnetocaloric material GD. This whole device is placed in between, just in front of this micromagnet, you can see, and which attracts the heat source, let's say the processor, laptop processor here in this case, and the other side is the cold head or the heat sink, which can radiate the heat to the air. So this is the to test the performance of this device. This is the test bench, lab made test bench, where this vibration is measured using this laser sensor. So this is the device, this is the micromagnet, and this is the GD film, the glossy, you can see here. So in 3D view you can easily understand this working principle. This is the metallic cantilever structure, this is the white ceramics on the top of this, the magnetocaloric material, and this cold source. This is the heat sink and the micromagnet here, and attached to the heat source. Yeah. So when arranged in this way at a particular distance, they start vibrating or oscillating and can produce energy in this state. Okay. So in real operation, you can see the sound of the vibration maintained between these two hot source and cold source, maintained by the Peltier chip, and the temperature is controlled by this temperature controller. The position of the vibration is measured by this laser position sensor, and the corresponding output voltage is collected from that, recorded by the NI data card, and finally live plotted here. You can see the snippet of the data here. Here it is. So nearly peak to peak 1.8 volt potential difference is observed there. So up to here we have reached this thermomagnetic generator which can produce a sufficient of energy. We can proceed further to have better efficiency. What happened in case of thermomagnetic generator? The thermal energy first converted to the magnetic energy, using the magnetic energy converted to the mechanical energy, and from magnetic energy to the electrical energy. Due to the presence of this intermediate state, the efficiency decreases as the possibility of losses increases. Now the efficiency can be increased if we can transform this thermal heat energy directly to the electrical energy, and this can be done by using an electrolytic material. Electrolytic material are the materials which can show adiabatic temperature change upon change of an applied electric field on it. So, and vice versa, means it can on abrupt field temperature change, it can produce potential difference across it. So if we can place an electrolytic material or film, let's say terpolymer or PVDF film on this surface of the MCM, let's say on GD, so the vibration of the magnetocaloric material can provide the driving force here, and the electrolytic material which can drive the electrolytic material in between the, changing the contact in between the hot source and cold source. As a result, its temperature of this electrolytic material will change abruptly from hot to cold, and due to this change of temperature it can produce electric field across it, which can directly produce electrical energy from this thermal energy with better efficiency. Now to have this best performance, we have to decide which is the best electrolytic material with highest efficiency. For that we have chosen two best available candidate. One from polymer family is PVDF terpolymer, another one is strontium 2 barium titanate at BSTM. So this is BSTM is obtained as MLCC multi-layer ceramic capacitor, and this is the thin PVDF, and measured in this way. The temperature was measured using the thermal probe here, and this is our instrumental setup. Here the sample was used as a capacitor structure, and the temperature was measured by the thermal probe here directly, and the corresponding to the applied custom signal obtained from this voltage amplifier corresponding to the signal generated from this signal generator, and the voltage across it, the potential difference, and the current through the sample, and also this temperature was recorded with the data NI data acquisition card, and data was recorded and processed further in the PC. The real device, you can see it here. This is the real device where this is the sample holder, and all these are the driving instruments. So for a better view, this is the schematic diagram with instruments. Here you can understand easily. So finally the data recorded in this NI data card, and finally stored in the PC. So to mimic the ideal operating situation where the samples change its position from hot source to cold source, or the field in case of this thermomagnetic generator or hybrid thermal generator, for in case of solid state cooling, direct field on or field off state, it is best to check by using square wave signal. But due to the capacitive nature of the sample, we have to limit the ramp of the field change to a finite limit instead of the infinite sudden jump, to limit the current as it can damage the sample. So this is our signal profile, and by using the signal, this was our obtained ferroelectric property of the both sample. Here the blue one is this for corresponding to the BSTM. A nonlinear nearly saturated ferroelectricity is observed here with a strong high polarization value of 227.6, and upon field removal it retraces back nearly on the same path, having an extremely small area inside it, whereas correspondingly in the same field the polarization increases for PVDF nearly linearly, and shows a nearly broader area inside it and decreased it, showing a very small amount of polarization, maximum polarization compared to the BSTM, that is 22.5. Anyway, if we increase the field further, the BSTM fails because it shows a breakdown at 39 volt per micrometer. So we cannot go further. That is one kind, can be said, the limitation of the BSTM. Whereas the PVDF can go much higher voltage, the showing the breakdown nearly 110 volt, and can easily performs up to the voltage of field of 100 volt per micrometer, where we can see a much higher polarization with 66.3 with some nonlinearity, although this polarization is still much smaller than the value of the corresponding to the BSTM. So this area inside is much prominent than the BSTM, which actually represents the total loss in the sample, which is prominently observed to be higher in case of PV area. We'll discuss it later. Before that, we can see the electrocaloric property here. So this is the temperature variation with time corresponding to the square wave signal as provided shown in the before for the both BSTM and terpolymer sample. We just before and after applying the field means this is the adiabatic temperature change during this ramp. So this adiabatic temperature change from each pulses are recorded, extracted, and corresponding to the field, the variation is plotted here. We can see a nearly linear increment of delta T is plotted here, observed here, with a highest value of 2.14 at 20 degrees Celsius here at the maximum field of 30 volt per second. Whereas for the same field of 30 volt per second for PVDF, its value is nearly 0.4 degrees Celsius, much smaller than the value of BST. But as already said, the BSTM can sustain up to a strong higher field up to nearly 100 volt per micrometer. Here it shows nearly more than double of the value, this value 4.91, so which is sufficiently high in this case. So after that, as we said, this is the loss calculated from that area. This is the max value is shown to be nearly 22.2 kilojoule per meter cube, but in case of PVDF it shows nearly 50 times, so 966.5 kilojoule per meter cube, which is sufficiently high. So in this table, it is, the value is plotted, all the temperature, delta T, adiabatic, and the loss, dielectric loss, tan delta is also plotted. So it shows a much smaller value, 0.004. So in case of PVDF, it is much higher, nearly 25 times higher. So anyway, so we see for PVDF as the delta T increases, also the loss increases too much. So to get a combined effect which is more efficient in this cooling cycle or something, we need to define a cooling efficiency vector in this way, combining both the effect of the loss and the adiabatic temperature change and plotted against the corresponding field. So here in case of PVDF, we see the maximum value was obtained near to the 80 volt, but before of that, though the adiabatic temperature change increases, but the loss increases so high, so this efficiency decreases, and at max applied field of 100 volt per micrometer, the efficiency is 9.4, whereas at the max field of in case of BSTM, it is nearly 37.7%, which is 4 times higher than the PVDF. So in conclusion, we can say better flexibility means the PVDF is better flexible or self-sustainable. In this case, PVDF is better. Also, the higher operating field is sustained in case of PVDF, but in context of higher capacitance, polarization, and lower loss is obtained in case of BSTM LCC. But the higher adiabatic temperature change at the same field is higher in case of BST, but at its max capability, PVDF is better here. But the combined effect of lower loss and the higher adiabatic temperature change, we obtain the higher electrolytic cooling efficiency. In that case, BSTM is better than PVDF. Thank you.